Okay, so the first thing to practice is units and conversions. And this is very important for the FE exam. It comes up a lot, and you can get the answer to some problems just by thinking about units and trying to come out with the right unit in the end. So this is a very useful skill, even for problems that are not directly related to unit conversions. Okay, the first problem here is convert 4 miles into feet. And we're going to use that 1 mile is equal to 5,280 feet. So we're going to do 4 miles and multiply that by our conversion factor, 5,280 feet divided by 1 miles, we'll say. And here you can see that the miles cancel out, and when we multiply this out, we are left with 4 times 5,280, which is 21,120 feet. And so that is how many feet are in 4 miles. Then moving on to the next one is convert 1,200 square feet into square meters. And we'll use that 1 foot is equal to 0.3048. It's probably too precise, but 0.3048 meters. So the first thing that we'll do is we'll take 1,200 square feet, and this one we can't just multiply straight across. We have to be sure that we have the same units. So we're going to have 0.3048 meters divided by 1 foot, but we need to square this so that we have meters squared and feet squared. So these will cancel, and we'll be left with square meters, and that will be equal to 111.48 meters squared, or square meters. The next one, we're starting to get a little applicable, but still converting units here. So how many calories would a 150-pound person burn by walking up a 500-foot hill? Assume all energy goes into gaining gravitational potential energy. So that one we can think of the energy equals the mass times the gravity times the height. So from there, we need to get all of our units in the same proper units. So we'll convert the pounds to kilograms and the feet to meters. So for our mass, we have 1 kilogram is equal to 2.2 pounds. So we have 150 pounds. Then we're going to multiply, and we want to get kilograms eventually. So we'll have our unit conversion with kilograms on the top, pounds on the bottom, and this is where we'll cancel. Okay. Gravity is actually okay. Then our height we'll do next. Okay, so we need 150 divided by 2.2, which is 68.18 kilograms. And then for our height, we're going to take 500 feet and multiply by, we want meters, 1 meter divided by 3.3 feet. So the feet will cancel. We'll be left with meters, and that will be 151.52 meters. And then we can calculate our energy, which is mgh, which is 68.18 kilograms times 9.8 meters per second squared times 151.52 meters. And so this will come out to 101,197, and this is actually joules, but that would be, or kilogram meters squared per second squared, but that's technically joules. Okay, then in order to convert that into calories, we can see here that one nutrition calorie is equal to 4,200 joules. So we'll just take our 101,197 joules and multiply by 1 calorie divided by 4,200 joules, and this will get our units to cancel, which is what this is all about, and we will be left with 24.1 calories. So a 150-pound person that walks up a 500-foot hill or gains 500 feet in elevation due to their own work will burn 24 calories. That seems kind of low. Okay. A person runs 7 miles in 1 hour. How many minutes does it take to run 1 mile? Okay, so what we want in the end is we want minutes per mile. So if we start out with, we want to get miles on the bottom. So let's go 1/7. 1 hour they can run 7 miles. We'll multiply that by 60 minutes and 1 hour, and this will give us 60 divided by 7 minutes per mile. Which that is 8.57 minutes per mile. So they're running a 8.5 minute mile almost. Okay. Now this one we're getting a little more engineering. A simply supported beam with flexural rigidity, EI, is 200,000 Newton meters squared, and it's loaded to create a deflection of 0.02 meters. So we're going to use the deflection, which is calculated here, for a uniformly distributed load on a beam. And we're using an L of 4 meters, and we want to solve for the load, W, in newtons per meter. So this is where this type of problem we can track our units, and it'll help us with our unit conversions. But it's also an engineering problem, which is useful. Okay, so here we go. We're going to have delta equals 0.02 meters, and that is going to be equal to 5W. We know that L is 4 meters, divided by 384. This is times the EI, which is 200,000 Newton meters squared. Okay. Then what we know is we know that W should be in newtons per meter. Okay, so let's go ahead and solve for W. W equals okay, 384. Sometimes it's helpful to do the numbers first, and this should also be to the 4th. Okay, so let's go ahead and do the numbers first. So we're going to be left with 1,280 W. That's just multiplying, bringing the 4 down and multiplying by 5. And that's over 76. That's just multiplying 384 and 200,000. Okay. And this would be, right now, we have meters to the 4th here, and W is in newtons per meter, and this down here is still Newton meter squared. Okay, and over here we have meters. So we could technically check our units to see if they're coming out correctly. So this one will actually drop down here, and we'll get a meters cubed here. And so then if we cancel here and here, we'll just have meters left up here, and then our newtons will cancel, so we just have meters, which is the same, which is good. So that means that this will work, it makes sense. But now we can solve for W, and that's going to be 0.02 meters times 76 million. The numbers really kind of don't matter here, it's just about doing the unit conversion. That's the purpose of this problem, but that's all right. Okay, so let's be sure that we got newtons per meter left. It looks like we will. When we combine this one and this one, we get meters cubed. So we'll have just meters on the bottom, so it's newtons per meter. And our final answer, just for fun, will be 1,200 newtons per meter. So that's the load, the distributed load, W. If we had a beam, that's 4 meters in length. That would be the distributed load that causes it to deflect. 0.02 meters at midspan.